we're delighted to have Adolfo Grushin from the Institute NAEL at the University of Grenoble, who's going to talk to us about some quantum physics out of the hat.
Yeah, so thanks. I want to thank the organizers for inviting me and letting me speak about some very recent work. Actually, we managed to make it to the archive by today, so I'm really, you should definitely, I should, acknowledge the hard work was done by Justin Schirman and Sama Franca. You see faces later on. So, I think the audience is made up of a lot of people. So I'm going to try to use language that might not be, exactly physically sound. So the physicists in the room, please forgive me a little bit for the purpose of pedagogy. I'm going to allow myself to do that. And hopefully by the end of the talk, you will see you understand what's going on in this picture. If not, you can ask me for the video and you can maybe make a nice lamp or something. So I'm going to start quite basic. What do we do in our group? So I'm a theoretical solid-state physicist, basically, and we try to understand how materials conduct, essentially. And so we all have in our heads what's an insulator, and the insulator I'm going to use for an example is air. So if you have air, you cannot conduct electricity unless you have a really, really strong amount of energy. And actually, the minimum amount of energy you need, we call that the gap. That's kind of a technical term. Now, for metals, in contrast, you don't really need that much for them to conduct. In fact, they're shiny precisely because when light hits them, it kind of creates little currents that reflect light. And so, in this case, we say that the gap is zero. So that's the kind of the technical way we think about the difference between metals and insulators. Now, it turns out, and this is kind of what my group focuses on in Grenoble, there's something in between. And this something in between has created a few Nobel Prizes along the years. And there are some materials that are actually metallic on the outside and insulator on the inside, which is a little bit weird. You could say, oh, maybe you can scratch out the metal at the top, but in fact, you cannot. And the reason is quite robust. It's hidden in the world topological. Topology, in this context means that there's some global property of the electrons' wave functions, or the way electrons kind of behave collectively, that guarantees that there's a metallic surface state. And you have to imagine that this can happen in 2 dimensions as well. So you can have an insulating bulk and something running around the edge of a 2D sample. And so my group kind of studies these. And in fact, the way these materials have been known for a while, and what we're doing is trying to understand how they survive disorder. I just told you that it's really hard to eliminate this metallic thing out of the top or the surfaces, and the insulators we kind of look more like that, very amorphous, very disordered, non-crystalline at all. And so that's kind of how I got into looking at aperiodic structures, basically completely not periodic, not crystalline by any means, looking at amorphous systems. That's kind of what we do in our group. And these are the main players. Also, one of the organizers is involved. We all had this idea of what would happen if we put electrons on the hat. So that's kind of what I want to tell you about. Before I go on to the details, I want to say a few more things about topological solids. Why should you care about them? It turns out that in the realm of crystals, many materials are predicted to be topological. In fact, more than half. So these have not been systematically verified experimentally, but there are many that have. But these are recent predictions and recent calculations that indicate that this could be the case. So this includes materials that you might or might not have heard about or care about at all. This muscelinide is a very textbook example. You say, what do I care about? So if you ever drank wine, you probably have put it in some wine fridge, or you should. I'm not French, but now I have to endorse France. You have to treat wine carefully, so you have to store it at temperature. You need a cooler. In this cooler, there are thermoelectrics, and those thermoelectrics are basically this family of materials. So very important. There's bismuth. Bismuth you might not use at all, but it's kind of pretty, so it's a very nice example. Kind of has conducting states around the hinges, which is kind of interesting. And even salt. Salt, it turns out it's believed to trap some charges This remains to be seen, but at least there's a theoretical prediction that sodium chloride, at least the structure, traps charges at the corners, which is some manifestation of the same phenomenon. Now, how does this look really like? How do we study this? Well, we ask how the electron's energy kind of changes with its momentum. How, if you want, how fast they move. And if you look at that, you can shine essentially light and extract electrons from these materials, and you get plots like this, where I plot energy versus momentum. So I get if you want group velocity of the electrons in some sense. You get a lot of weight here at the bottom, a lot of weight here at the top, and something that kind of crosses and connects this very shiny blobs in a way that looks kind of linearish and cone-like. And this cone-like dispersion is kind of very special. It looks like the dispersion relation. We call this the dispersion relation. It looks like the dispersion relation of relativistic particles, like the photon, for example, where the energy is proportional to its momentum. You think of X-rays, they're very powerful, so they have very small wavelengths, and this is kind of a very large momentum. So that's why the energy kind of increases with momentum for light. And so these particles at the surface of bismuth selenide in particular look really like zero relativistic particles, if you want. Now, this was not the first, so topological studies were actually not the first example of Dirac. We call these Dirac cones because they're used by Dirac back in the 30s. In fact, you might have heard about graphene. Graphene is a two-dimensional material, an hexagonal lattice of carbon atoms. It's realized in the lab. And in fact, if you plot, actually, a very good model that I'll be using in the talk, but if you don't understand the math, it's fine. It's basically saying graphene's properties of how electrons propagate are well captured by considering electrons to have a certain probability of hopping between nearest neighbors and nearest neighbors only. And this hopping probability is T, so you can imagine electrons kind of hopping around with certain probability. And in fact, this if you plot with use this model to plot the dispersion relation of graphene, which is the energy versus the momentum in a certain path in momentum space, you can have different directions of momentum. You'll see this really interesting crossing that, if you would plot in 3D, would be indeed a Dirac cone. And if you make a cut at a certain energy, you'll see that exactly the six-fold symmetry of graphene kind of is reflected also in this momentum space representation, and you'll have these kind of Dirac cones around these hexagons. So if this kind of repeats, since the lattice is periodic, it's also periodic in K-space, and this kind of, you should imagine this as repeating infinitely many times. Right, so if you do the same experiment as I was saying before, you'll see that it actually matches really, really well. So this is experimental data. So this is how well we understand graphene. This shining light, eject the electrons, and you put it in the dispersion, and you can really, really fit it nicely, and same with the constant energy cuts. Okay, so, graphene is a real material, but we're not here for graphene, but we're still here from a point of view of 2 dimensions. So what if the hat was a 2D material like graphene? What if electrons could move in the hat? What would that lead to? And so I want to ask, how similar is this to a crystal? Because we know that, kind of comes or follows a little bit the hexagonal lattice. And how, we could also add how different it is from other quasicrystals, because people have been putting electrons in quasicrystals for a long, long time. And so, again, I apologize for not being very precise mathematically. I am, as people have been referring to, I'm a non-mathematical person, like a non-mathematician. That's the word, non-mathematician. But anyway, so if you take, for example, this. I'm going to call it a quasi-crystallite, just referring to a finite system of this styling. You'll see that you can define sites at the vertices. This is what people have done already since the 80s for different quasi-crystals. And this is just one of these tiles, one of these construction rules in the paper they refer to as this H tile that you can inflate. And so now I'm going to exactly do the same thing. I'm going to try to ask what is this dispersion relation of the electrons in this system. Now bear in mind that now you don't have periodicity, so this means that K space is not exactly very well defined, but still, it's still meaningful to ask whether some electrons do have a well-defined momentum. And in fact, if you plot a spectral function, which is how we call this plot, you'll see that there is exactly this six-fold symmetry that has been alluded to yesterday in the structure factor kind of appearing again with certain extra features that I'll mention to you in a second. But this is already quite amazing that not only that it's six-fold symmetric, which might be expected, but also that it resembles so much graphene. And in fact, it resembles so much that if you make a cut and look at this cut as a function of energy, as I was doing before, you'll see that if I use graphene to kind of fit the dispersion relation that I see, it matches kind of well. So there are many features, not all, but there are many features in particular, these kind of crossings here at around minus 0.2 that are really reminiscent of Dirac cones, which is kind of amazing. Now, so in this sense, the hat, it seems that it kind of knows about this hexagonal lattice that was already present in the foundational paper, I should say. But there's a little twist to this, which is this is actually not the graphene lattice we have used to fit the band structure that you just saw, this dispersion relation. We actually used a little denser version of the hexagonal lattice that has more points, more lattice sites sitting at the sides of the hat. So the sides of the hats are here in blue. Whenever you don't see the blue, it means that there's either one of these white sites, which are the graphene sites, on top of it. And there's some, of course, away, but like more than half are kind of sitting on top of the hat sites, and this seems to be the best fit to the band structure, to the dispersion relation. We do have to add some extra terms, not only nearest neighbor, but also next nearest neighbors, because the model is not entirely symmetric. But nonetheless, it's really nice that this kind of works. Now, there are also differences with graphene. And it has been mentioned a lot, like the concept of chirality, so I want to kind of redefine it for physicists, the way we think about it. And the way I want to think about it is the absence of reflection symmetries. And I'm thinking about it, this reflection symmetry, I'm going to apply it to the full lattice, not only to a single hat. I'm just going to take the full lattice. So let me give you an example. Typically, we use shoes, hands, whatnot, but again, I am employed, I'm a public state employee in France, so I have to use Paris. And in Paris, although I don't live in Paris, but I learned coming here actually. I took the train and I passed by Paris. And in Paris, I learned that this is a friend, and they told me actually the name of the neighborhoods, which are the arrondissement, and they called they're numbered, and they're actually numbered in this clockwise sense. So if you mirror it, it actually is not the same. So there's some chirality to that, in fact. And so this is kind of illustrates that Paris doesn't have mirror symmetry, so it's chiral. Graphene, on the other hand, is not chiral. Graphene has reflection planes, and so if you flip, you may choose different reflection planes. Here I show one. You flip it and you get the same thing, so it's not chiral. Now, the hat, on the other hand, is chiral in this sense. So one could ask, because if you realize this model in a material, you might realize it with a certain chirality, and so it might have different properties. And in fact, it does. So if you look at this spectral function plot, again, like we fix an energy and plot the function of momentum in the x and y directions, you'll see that the two look quite similar. They have this six-fold symmetry, but there are certain widgets that don't actually fall into each other. And this is really clearly seen if you kind of subtract the two images. And this really spreads around what we call the quasi-Brian zone. Of course, it's quasi-periodic, so it's not entirely periodic, but still this tells you that the two things, the two enantiomers are not exactly the same, which is expected, as I said. And this is relevant for physical phenomena, because if you shine light and and it has a certain polarization, you actually can rotate the polarization of light just because the lattice is not mirror symmetric. Another difference with graphene are zero modes. This is a little bit more technical, but let's see if hopefully I can make myself understood. if you plot the energy of all the states in this plot that I just sent, you forget about momentum. You just plot it as a function of energy, and now you count the number of states you have at a certain energy. You'll see that at 0 you get this peak, and this peak we call the zero modes, and there are a number of them. In particular, in this H2 realization, there are 8 zero modes. It means that the states that I have here exactly are annihilated by Hamiltonian. So there's and this zero modes in quasicrystals have a long history, as I mentioned in a second. But it's interesting that they appear also in the hat. And this is not something unique to this H2. Actually, you can go through all the generations, all the different types of tiles. And you'll, or metatiles, maybe is a more precise term, I don't know. You'll get different numbers. And so one question would be like how you count this number, like how do you predict them, and whether how generic is this? So you see that it's kind of generic, but it's kind of a little bit looks like a little bit random. And in fact, if you look at the spread of this, like how the electrons, let's say, or the wave function of the electrons in technical terms, the local density of states looks as a function of space, looks kind of spread out. And this is a little bit in contrast to what happens in the Penrose tiling, which these zero modes also exist, but they're kind of localized around certain features. And this is not happening at the hat. So this is a nice, interesting difference. And so actually, Felix, one of our organizers, has looked at the robustness of these modes, which is also kind of different in both systems, it seems like. Now, one could think that because the hat is made out of like smaller tiles, smaller arrangements of tiles, you would think that these zero modes are kind of inherited from previous generations. And this is partially true. You can see that these, for example, H1 tiles kind of have similar motives, but in fact, it's not totally true. Because, for example, the T1 tile, if you the T1 quasi-crystallite, as I wanted to call it, has no zero mode, but here there is some weight on the T1 tile. So there is something more subtle going on. And what's going on, in fact, is that depending on how adding or removing hats can add or remove zero modes in very interesting ways. In particular, if I remove a hat from this T1 quasicrystallite, I'll get a zero mode that has the real part of the wave function, or like how the electron wave function kind of modulates in space, will have 1, 0, minus 1, 0, 1, 0, and so on in a loop that is of size 4n, where it is an integer. Now, not all loops follow this, but they do follow the fact that this is kind of the simplest zero mode one can think of, or even Sutherland thought of. But what is true is that the number of zero modes is still the number of paths that you can make with zero total neighboring weights in this vertex model. Okay, so now physicists like to add knobs to study electrons. They just try to see how they react to different things. In particular, magnetic field is a very simple thing to add to study in the lab. So we thought that we could try to understand this. So what happens to electrons in magnetic field in general is that as they circle a plaquette, or in this context, in this conference, I should call it tile, but as you circle a plaquette, you pick up a phase. So the wave function doesn't go to itself as I circle one plaquette, but it picks up a little phase that depends on the magnetic field. It actually is the magnetic flux per plaquette. And so, for example, if this F is 1/2, it'll pick a minus sign as it goes around the plaquette. This is called the Hartmann-Bohm effect. It's known for a long time. Now, you could plot how the spectrum, meaning the energy, changes as a function of magnetic field, and this is what I show here. It's a huge mess. But I want to, and this is expected, so normally you get a huge mess. But the thing is that you notice, first of all, there are certain gaps. I'll go back to that in a second. And also notice that I only plot from 0 to 1. And the reason I can do it is that the hat is a monotile. And this means that there's only one area I can choose. There's only one plaquette, and so one plaquette only has one area. And so I can normalize this flux over that area. However, in the Penrose tiling, you cannot do this. And you have two areas of, in general, incommensurate area, and so the spectrum is quasiperiodic. And so this is a real difference between monotiles or aperiodic monotiles and tiles with more than the one tile. Yeah, tilings with more than one tile. Now I'm going to show you a little video animation that moves. So I'm going to move the magnetic field from 0 to 0.5, and you're going to see how the zero modes change, because the zero modes actually still survive. You still see kind of a line here. And so let's see how this looks. So as you move, they kind of evolve a little bit. They start finding some structure, and as they move right at the half flux, so pi flux per plaquette, you see that they are localized exactly at the anti-hats. So this is quite a cool thing, and this is kind of the lamp I was showing before. Somehow, by tuning the magnetic field, you can find your anti-hats, the hats that are mirrored with respect to all the rest of the hats. And not only that, the number of zero modes, it seems, this is an observation, we haven't proven this, but it's kind of generic of all the systems we've seen, is that the number of zero modes equals the number of anti-hats. And this now starts resembling a little bit more what the Penrose styling does also in magnetic field. It kind of localizes around certain motives. So this is, in the sense, you kind of recover a little bit more similarities with the Penrose styling. And now, these zero modes, if you look at them, actually, because you need to acquire a certain minus sign as you go around the plaquette, these anti-hats exactly have the exact number of sites, such that if I introduce one defect, now remember that before I had blue, red, and so on. So 1, 0, minus 1, 0, and so on. Here I have some defect in the sequence, and that's precisely because I need to acquire a little minus sign as I go. And these are the simplest loops, and apparently these are the ones that give you all the zero modes. It looks like. So 1 zero mode per hat, because you have one of these loops one zero mode per anti-hat, because you have one of these loops per anti-hat. Okay, so to start, to keep studying the magnetic field properties, let me zoom in into some part of the spectrum. This is not really a special part. It's just easier to analyze just like a small part of it. Just zoom in. You see all these gaps appearing, and in fact, these gaps, some of them are completely empty of states, but some of them, in fact, have states. So here I'm showing the states that are essentially have weight on the bulk. But in these white regions, you can have either no states or states that are localized at the boundary. And there are many of those, and like here I show one. And what's special about these, and here is what the topological insulators come back at you, is that if you put two contacts, let's say you grow this material, if it existed, and you apply it to contacts, and now you measure how it conducts. It turns out that in all these gaps, the conductance is exactly E squared over H. It's quantized. So it doesn't depend on anything. Like if you add this order, it will still be E squared over H. There's literally just a universal constant that determines the conductance in this thing. And the reason is that there is actually an edge mode that goes, so this is the density of state that you're seeing. This is not only localized at the edge, but it also has a chirality. It actually moves electrons from the left contact to the right contact, or vice versa if you change the voltage. And this is actually known. It happens in all 2D materials, but it's also in the hat. What's kind of nice is that you can find integers that kind of label these gaps. We call them topological invariants, and they essentially count the number of edge states. So here you would have 1, 2, 3, and so on. So this is I won't get into the details of what is topological about it, but essentially it's determined by a global property of the wave function of the electron. Experiments. So this has been some recurrent theme in this. Like yesterday, there's some questions about engineering applications. Or are we going to see any experiments? Well, we can, and this is the good news. Let me first start with what could be done. So in solid-state physics, there are things that are called artificial lattices, and people have been playing with that for a long time for many purposes, in particular to do topological insulators artificially. One of the things that you can do is you pick up a material, in this case it's a superconductor, but it doesn't really matter. You put some atoms, we call them, so some atoms on top of this material, and you can literally take that atom and drag it around. For example, here, if you see this atom was isolated, now it has like 3 other neighbors and so on here, and literally make whatever you want, like that. And this has been done for years. The technology is very well developed. People have done like fractals. There's no reason why a quasicrystal cannot do that. So this is quite cool. The other nice thing is that you could do what people call metamaterials, and these can be of different types. But for example, photonic quasicrystals, this means that you pick your favorite quasicrystal, and this is really an experiment that has been done in this paper. You pick a quasicrystal, and you propagate light through these waveguides. And you see that these waveguides are kind of like wiggly. So first of all, you see that they're next to each other, so they can couple. And so that's how they couple through Van Allen modes, and they can affect the motion of light, let's say, long in 2D. They don't like travel independently. But also these wiggles actually simulate the effect of an effective magnetic field, because as you propagating this wiggle, the propagation of the ray kind of picks up a phase, and this is really reminiscent of what I was telling you before. There are phases that you have to acquire, and it's a little bit different, but still it's very close. You get similar physics. And as I was saying, there are many other options. Even electrical circuits can do things like this. In electronics, you can have waves propagating at a certain frequency, so that's the same type of idea. You can have acoustic or mechanical metamaterials. So there are certain options, but these are kind of my two favorites. And kind of in the last couple of minutes, I'm going to tell you a little bit of an unexpected surprise. So thanks to this conference, so I was. I have some friends. So Grenoble is very well known for geoscience. I'm not a geoscientist at all, but I have many friends because the geoscience lab there is very large. In fact, I think yesterday somebody said that MIT is the Waterloo of the United States. So ISTER is the geoscience lab. So MIT is like the ISTER of the United States. ISTER is the Institute of Science of the Earth in Grenoble, and somebody already asked whether you could, they were thinking about telescopes, but the underlying idea of the question was, is there anything that aperiodic arrays of things can help you with that you're going to do with periodic arrays? So here's a possibility. We're still exploring this, and as I say, this is we met at a bar. I told my friend Aurélien about this conference, and we were like, oh, wait a second, but I think this is kind of cool for so this was 2 weeks ago, so forgive me for the rough details. But he thought, yeah, maybe we can. So one of the things they care about is magically you have a seismic wave. You want to know where the epicenter is with high precision, and one of the ways to do it is you put a set of arrays. At a certain, you don't really necessarily know the angle or the direction of this wave, and so what you do is you try to do this beam forming, and what you do is essentially one very optimized version is to put the detectors, which are these blue dots, in a spiral form, so that you have many rays connecting them. This kind of optimizes the beam reconstruction. So what they do is they say, okay, imagine I shine this seismic wave in all directions, kind of detect it, and this is what you see here. If I wouldn't be able to detect some part, it would be dark. So this is measured in slowness, which is the inverse of velocity, but that doesn't really matter. What you have to know is that if the circle is very nice and uniform, then you can detect very well. Now you can look at that triangular tiling, and the triangular tiling has a lot of redundant information, and that brings a lot of artifacts. So you don't exactly sample what you want. You have a lot of artifacts. If you take the hat, it actually doesn't do very well. So the hat also introduces artifacts, and for a very good reason, because it falls on a hexagonal tile. However, if you take tile 1-1, and here's the surprise comeback of the Spectre, if you take tile 1-1, it actually does a pretty good job for the same number of detectors. And so actually, Aurélien made this really nice video that I'll show, which is you're seeing how the beamforming capabilities are here, like how well the circle is represented depending on which part of the family of the tiles you have. And here you see kind of the density of rays in the azimuthal direction or the radial direction, which is some measure of how well these things can do. Now, this might seem a little bit crazy. I'll just put this up. This might seem a little bit crazy, but in fact, there's beamforming, which is what I just showed, but there's also tomography, which is, imagine you want to know what's actually underneath the surface of the Earth. That's kind of hard. You need to know how waves propagate and how they diffuse, how they decay. And so this is another type of experiment that I'm not showing. But so in beamforming, you want them to be distributed kind of aperiodically because you want to maximize the number of rays, essentially. And so this spiral is very efficient. But now if you want to do this tomography, this like knowing what's underneath you, you actually want a periodic array for reasons that I won't get into and I probably don't understand as well as Aurélien does. So I just say this. And so these monotiles are kind of in between the two. And so what's nice about them is you could do in principle both experiments with a single array, which is kind of nice. And so I think this answers kind of the question of what these things are good for. Here I'll just leave you with the conclusions. There's some interesting similarities with graphene. Many of the features can be captured. There are interesting features in the zero modes that can detect. There are anti-Hat detectors as a function of magnetic field, and also more or less expected transport phenomena that we've seen in other quasicrystals as well. And then the bonus is the seismic detection. So with that, I'll take any questions, and thank you for your attention.
Great, thanks very much for that lovely talk. Question there.
Thank you very much. This is very interesting, and it's one of the talks I've been looking forward to in this conference. So, as you said, like there are zero modes that you mentioned, both in the bulk and on the edge of the timeline, which I find very interesting. But I want to focus on the edge modes that you found. Not the direct cones, but the stuff on the edge.
Like
so,
this picture?
Yes.
Yeah, okay.
So, from what I know is that like there are like non-topological edge modes that can occur, which you can just insert like local perturbations to cap them out. But to really pin down what makes them topological, typically people need to find like a bulk topological invariant.
Yeah.
But as you said, you mentioned that because the tiling is not periodic, there's no notion of bulk. So what would be the corresponding, what would you think the corresponding invariant?
Yeah, so actually, this is one of the nice things about studying amorphous topological insulators, that we're very well prepared to do this. There's in fact a lot of, so you can take the topological invariants used for crystals, and not all, but many of them you can define in real space. And in the following way, you can take a quantity that is local, and at each side it won't tell you that you're topological, but if you average it over the bulk, if you take a sufficiently large part of the bulk, it will be quantized. And you can show from kind of complicated K-theory and things like this that even in real space they will tell you, this average will tell you the topological invariant that if you were periodic, it will be the same invariant.
That's the like the algebraic K-theory linear states.
Yeah, it's literally that. Like you can essentially, just to be a bit more technical, if you take the Hamiltonian and you take the position operator, something that is trivial, a trivial state will have those things. A trivial Hamiltonian will have, you could be able to commute those because you will be able to find a localized state with a given energy. So that's a trivial. You declare that as trivial, and now you ask, is there an operator that tells me how well these two things commute? And this is the localizer. It's been like, it comes from K-theory or like non-commutative geometry, and it's well known, and this is what people use for periodic systems.
Yeah, very nice. Just one last comment.
Yeah.
So there's actually another way to detect topological order, which is topological entanglement entropy.
Yeah, yeah.
Yeah. So maybe you can compute that as well. Like.
Sure. Yeah. Yeah. So topological entanglement entropy, you would have to have let's say real. So this is topological phases. Technically speaking, probably symmetry prediction. Okay, it doesn't have symmetry, but the topological entanglement entropy is useful for topological order. So those are systems that have actually interactions, anyons, things like this. So in principle, one could think this is something we have in mind, like to define strongly interacting models on these things, and perhaps depending on the phase you're looking at topological entanglement entropy probably is a good idea. Yeah.
So I'm not sure if I understood correctly. You had a certain density of states at flux 1/2. That was the same as the density of anti-hats.
Yeah.
And everything was localized from the anti-hats. And is the density of states constant as you vary the magnetic field, or?
No, it actually, so it's mostly constant. Actually, I could probably show the plot. So you see that they're it's kind of hard to see, but if you would zoom in here, it's essentially constant for a long time, and suddenly, like a lot of states kind of come down.
Okay, that's what I was going to ask. Basically, as you vary the magnetic field, where do the states go?
Yeah. So in fact, because here at 0, there are fewer states. There could be fewer states than anti-hats, and so I'm not sure if this answers where they go, but like they certainly come down from higher energies to be at 0 at white flux. Yeah.
Okay, thanks.
Yeah. Thank you.
So when you were saying that at half flux you end up getting these zero modes that live on the anti-hats. Have you looked at smoothly going over the kind of transformation from the hat to the 1-1 and then to the 2 ends, and then looking at where the zero modes go, if they stick around? Or?
So we have looked at the tile 1-1, and in the tile 1-1 you also have special rotated tiles, and if you would do this exactly the same, you also see that at pi flux, or like at half flux, you'll see the local density of states around those special tiles. Yeah. So it also works for tile 1-1. Yeah. I don't know how it evolves as you change from this family of tiles. We haven't done that, but we have done the tile 1-1. The tile 1-1 though doesn't have the graphene stuff because it doesn't like really fall on top of the hexagonal.
Yeah, thanks for the nice talk. One little comment and one question. So first of all, this talk showed why sometimes it makes sense to distinguish the hat-dominated and the anti-hat-dominated tiling, because it really shows these different chirality directions. Yeah? So sometimes for mathematicians that is hard to understand why you would want to distinguish them, and we saw that clearly why in some situations it might make sense. And the question I have, when you showed the surface state, if I'm not mistaken, that was for really a complete supertile, right?
Let me see. This.
Yeah.
Yeah. This is H3.
Yeah. Right. Now, as you can see from this picture, if you would continue with that, it would develop a fractal boundary. So the length of it, so to say, relative to the bulk size, would not scale linearly, but with some power, which would be the Hausdorff dimension of the boundary. So do you know what influence that has? And if you would not use a supertile, but just any patch, would you still see the surface surface
so
states?
the second question, the answer is definitely yes, because that's you definitely see an edge state no matter what shape you have. Whether you could see the effects of, I think those type of effects start appearing when you start adding disorder. And so how the critical theory, meaning how the edge state scales as a function of disorder, the conductance of the edge state scales as a function of disorder, perhaps I would have to think about that. I don't know exactly how the dimension enters, because the edge state conductance cannot change because of topological reasons. So it might be a little bit tricky to see how. And respect, regarding your first comment, from the point of view of the stock, actually, we don't really care that much that some tiles are the mirrored versions, because the whole that is in the definition I gave is chiral, in the sense that it's not mirror, and that happens also with the tile 1-1 as well. So both tiles, in my definition of chirality, both tiles are chiral. I was actually a little bit confused at the beginning when the second paper appeared. Like, oh, okay, but the other one was chiral. But it really means that if you flip it, you won't have the same lattice. And this is important for, as I was saying, light propagation. But both tiles have, in that sense, the same properties. Yeah. But it is indeed an interesting remark. I'll think more about the scaling. I don't know the answer right away. Yeah, it's a good one. Thanks.
So I think we'll defer any further questions till the lunch break, but let's thank Adolfo again.
Thanks.